Hello, my name's Chloe and I'm going to be talking about how we can aim for explainability when we design evolutionary agents. So one of the aims of artificial life research is to create simple models that reduce the complexity of a scenario, such as taking something from nature and trying to study it in closer detail to understand what's going on and to see what we can learn from it. But one of the troubles is that sometimes these models can still be pretty complex, and that means that there's some things that we don't understand about why agents are learning certain things or why they're evolving certain behaviors, for example. And evolving agents to learn complex tasks to achieve a goal is a challenging problem. And there are different approaches to design agents that can solve complex problems in a number of different ways, such as task decomposition or evolving modularity in a neural network, for example. But our focus is more on explaining why the problem is difficult in the first place and what we can learn from it. So the river crossing family of test beds has been used in the past to explore these kinds of problems. So what we're trying to do is actually look at why this problem is difficult in the first place and what we can learn from it, rather than how we can engineer the best solution to this problem. So our test bed is the river crossing task, which you can see on the left. And we've reduced it right down to explore one fundamental component of why this task is difficult. And we've reduced it down into something called the minimal river crossing task on the right, or the RC minus. So the original river crossing task, the RCT, is a 19 by 19 grid, and there is a river of water running down the middle of the test bed. And the agent's goal is pretty simple. It has to learn how to cross the river from the left to pick up its resource, its reward object, on the right-hand side. But the difficult thing here is that it has to learn how to cross that river safely. So it's got to learn how to pick up a stone and put it in the river to build a bridge. And this is what we've identified as the hard part of the task. It's a difficult thing for it to learn, and we want to understand why. So because it's a complicated problem, agents have a two-layer neural network learning architecture, so there's lots of complexity there. So we've reduced it right down into a 1x5 test bed. So we have our 3 objects, which we've identified as a fundamental core component of the learning task, so the building of the bridge. So we have the water on the left-hand side, the stone on the right, so it can build a bridge, and then we have our agent in the middle. And because our test bed is so small, we've limited the agent's movement into moving a number of moves right and then moving a number of moves left. So the solution space is actually limited to 12 possible valid solutions. So a chromosome for the agent is how many moves it moves right, and then how many moves it moves left. So we can actually map this out completely into a fitness landscape. So we can see exactly what the chromosome, the pair of numbers, what number of moves it moves, what this corresponds to in terms of fitness. And we can see that as the problem that we explore is the effect of a cost to movement on the agent's fitness. And we can see that with no cost to movement, there is a neutral landscape. So agents can wander around during evolution until they find the goal achieving fitness. And it's relatively easy to do because of that. But with a cost to movement, this creates a trap function. And we can see this clearly because as an agent gets closer to the solution, it actually gets a worse fitness. So it's kind of misleading. We can see that very clearly with these graphs. And what this means is that our agents are explainable. The example that we've looked at, the cost to movement, we can see exactly why agents behave in the way that they do. And this means that we can actually generalize the results from the RC minus, the minimal task, into the original river crossing task. So we can predict and understand the behavior of our agents. And that's a whirlwind tour of our paper and you can contact us at our email addresses there if you have any further questions. Thank you very much.